Okay, so that video helped hopefully visualize what we're talking about when we're doing divergence and curl. I really like his graphics a lot. So curl is basically how a vector field is rotating. And if you're given a vector field PQR, then you get this, there's this new operator. It's not really new, I guess, but it's like standing by itself. That if I said just a little upside down triangle, you're doing the partial derivative with respect to x to whatever is in the I component. Then that was like the shortest sharpened knife ever. With respect to y and the j component, and then z for the k component. So you'll see for curl, it'll literally say curl of the vector field f, and then you'll have the Dorito happening with a cross product to your vector field. Remember, when we're doing the cross product, what's the first row going to be? IJK. And the order is significant here. We're doing the operator, the Dorito operator, so you're doing the partial derivatives in the second row. And then whatever the values are for the second term. So F is a vector comprised of P, Q, and R. So when you do this, again, you can copy and paste the first two columns. It's easier when there's actual numbers to do it too, but what you're going to be doing is multiplying. You have in the I part of your vector, you're going to be doing the partial derivative of R with respect to Y. You're probably also going to do another one, so leave some space. And then we got J component's going to have the partial derivative of P with respect to Z. And we got the partial, in K we're doing partial derivative of Q with respect to X. And then we subtract going up. So you'd have partial derivative of P minus the partial derivative of P with respect to Y. That's going in the K spot. Minus the partial derivative of Q in the I spot with respect to Z. And then the last one we did the X to R. Or you might see it written like R sub Y minus Q sub Z, P sub Z minus R sub X, and then Q sub X minus P sub Y. that's what the curl is trying to set up a determinant where you're doing the partial derivatives to the vector field. And your curl is talking about like the rotation of the vector field at a certain point. Okay, so if the curl is equal to 0, then the function has a continuous second order partial derivatives. The vector field is a conservative vector field for that function that we were talking about before. And the vector field is defined in 3 space. There should be a comma right here. All right, so let's see if it's conservative, and we'll do the test for conservative in 3D being, is the curl of f equal to 0? Mm-hmm. For what?
For, say, just f of x, y, would that not be the case?
It could still expand if we're only in 2D, yeah. But, well, no, because you're not going to ever be able to do the curl of something in 2D. Well, I guess you could make the k be zeros. So you could do the curl, but you're probably going to do a different, the like partial derivative test when it's in 2D. What'd you say?
You can't do partial derivative test anymore.
Think about what that would look like for you.
You have to do 3.
I don't think it's gonna work the way that we think it's gonna work. Oops, I'm on the wrong row. Oops. Okay, so first putting in the I spot, I'm going to take the partial derivative with respect to y. I'm just going to write it out instead of putting it in vector form, because I think some of you, that might confuse you more than if I put the I with it and rearrange it. Okay, try to compute that. Okay, does this equal 0? No. Because it doesn't equal 0, and it should be a 0 vector, so like the things would cancel each other out and be 0, 0, 0. Since it's not 0, it's not conservative. It's really in differential equations when you'll learn how to handle something that is not conservative. Well, not so much in this class. Divergence. Divergence is a scalar quantity that measures how much a vector field is spreading out or flowing away. I think in the video he said like a source or a sink from a given point. Essentially indicating the net outward flow of a vector field at a particular point. So if it's positive divergence, that's what he called as a source in the video. It's moving outwards. And then negative divergence was the sink. Let's think of a sinkhole. And how we compute the divergence is, where can I write this? I know, the arrow's too big. The divergence of F is equal to that same operator, the Dorito, but now we're dot producting with our vector field. So it's essentially going to become partial derivative of P with respect to X plus the partial derivative of Q with respect to Y plus the partial derivative of R with respect to Z. All right, so let's calculate the divergence for this one. We're going to find the divergence of this vector field at any point. Again, the Dorito is all those partial derivatives. Dot producting with F is going to be x squared y, x, y, z, negative x squared, y squared. Which really gives us, we're doing the partial derivative with respect to x. So that first component of the force vector, force vector. Plus, because it's a dot product, so we're adding between terms. Partial derivative with respect to y to the second term, plus partial derivative with respect to z to the third term. So the end with the divergence theorem, you're not going to have a vector. Curl gives you a vector. Divergence gives you just some, I guess, a function, really, that can tell you a quantity at a point. Doing the partial derivative, you go 2xy plus xz. Thank you. So this is the divergence at any point. force field. Okay, so these concepts can apply in fluid mechanics, where F is the velocity field for a fluid, and the curl of that velocity field is the tendency for the fluid at a point to rotate about the axis pointing in the direction of the curl. If you learn about the right hand rule, maybe you have, maybe you haven't, I don't know. Here, we'll try to do a 3D situation. Here's my thumb. Here's my pointer finger. And here's my middle finger. So the thumb is your curl. Your pointer finger is the flow. And your middle finger is the divergence. Mm-hmm.
How does that help?
You gotta know your physics, I don't know. So if your curl is 0, that's being irrotational, aka not rotating. And the divergence is the tendency of a flow to diverge from that point. You could also think of it as like the net rate change of the mass of the fluid. So, if we have the curl moving counterclockwise, then the curl moving counterclockwise would have been negative. Curl moving clockwise would be positive. So it'd be like if you had maybe around a source, clockwise rotation would be the motion around it, like how much is rotating around that point. Versus clockwise rotation. My purples are supposed to be the curl, by the way. And then our divergence, this was like a positive divergence is the source. And a negative divergence is a sink. Mm-hmm. No, it's just the way I decided to draw like a clockwise curl. Good question. All right, now we're gonna go to parametric surfaces in their area. That the curl and divergence is kind of like a skill, like a operation that you need to have to be able to do the stuff in the rest of the chapter. And this one also, we got some skill build that we need to be able to get to 17.7. All right, so 17.6, we have parametric surfaces and their areas. So if you take a point UV from 2D space and a 2D domain, and you want to, it would maybe like be easier or more useful to plug it into 3 variable surface, then you're saying R is a function of U and V, and then you have now X, substitute X as a function of U and V, Y as a function of U and V, and then z as a function of u and v. So 3 variables, you have some 3 variable function, x, y, z, that you're trying to become a 2 variable situation. So take the points in 2D space, plug them into the functions in 3D space. So look at example 1. You have something in 3 space, I, j, and k, but not every component, but a lot of the components in that vector are described by just the 2 variables, u and v. So you can make a parametric equation. What would x equal? U. And y would equal u cosine v. And z is equal to u sine v. So right now, when I look at R, I mean, I personally can tell what it looks like, but I don't think that you know what shape this is. But if we can go into X, Y, and Z, you're more likely to be able to figure out what this is trying to be. So if we eliminate the parameter, I think the parameter that you can see pretty obviously would be X is equal to U. So everywhere that there was a U, we're going to substitute X. All right, when we have sine and cosine, what would happen if we squared them? Huh? Right, you'd be left with x squared. So you see how this leaves you with x squared, but what were we originally doing when we had this right here? What was this equation? Which variable was being squared? I think y was being squared. And then what variable was being squared here? Z was being squared. So if you had squared x or squared y and squared z, it would leave you with x squared. What shape is thing squared plus thing squared equals thing squared? I think I heard it. It's a cone. This is a cone, and it's a cone opening in the x because the x squared was the thing like isolated. So that's one way to go from 2 variables to 3 variables. Now we can also go from 3 variables to 2 variables. So we want to rewrite this. Currently, this is written like x is equal to a function of y and z. just as like, sorry, I probably should write these as descriptors of what we're doing in each example in the future, but that's basically what we're doing. Okay, so to go from an equation of 3 variables to a vector of 2 variables, right now I'm going to leave x equals as 5y squared plus 2z squared minus 10. And x is written as a function of y and z. So what are the parameters that x is like dealing with? What are the variables that x is in terms of? Y and z. So leave it as like y is equal to y and z is equal to z. Now write it as a vector. This is something that seems so basic, but people struggle to like do this conversion at the jump to then do the calculus to these functions. So we want to write this as a vector. Taking it and writing it as a vector, where instead of being a function of y and z, we're writing it as a vector of y and z. So what do you think the I component would be? It's usually whatever x is. I think so, Chloe. I can't quite hear what she's saying. All I hear is like mumbling from that side of the room. And then what do you think the j is? Huh? Y. What about k? Z. All right, on the sphere, a little more complicated. It's a sphere. It's not really like as easy with spheres to just solve for one of the variables. It's a better idea to get to be in terms of spherical coordinates. So rho, theta, phi. What would rho be equal to? Yes, rho square 30. That's constant in a sphere. Sphere is just a ball that stays at, having a radius of square root of 30. What is x in spherical? Rho sine phi cosine theta. Y is rho sine phi. Good. And z is? It's the different one. So really we're going to have square root of 30 sine phi cosine theta. Square root of 30 sine sine. So what would r be a function of now, or a vector function of? What are your two variables? Find theta. Typically theta comes first, so that's why I'm writing it first. Kind of running out of space here, so I'm gonna overlap it. Okay, try to think about how to do it in cylindrical. Alright, hopefully you got the cylinder down. If you have some parametric surface, which the parametric surface that we're using is this R, being a vector function of u and v, and we want to do a tangent plane to that surface. Then you can take the partial derivative of R with respect to u. And v. And do the cross product between them. So as long as when you take the cross product of something, it doesn't equal 0, then it yields an orthogonal vector. Think about if you were doing like, this is like R, U, and then you have R, V. If their cross product equals 0, that means that they're actually parallel. It's like a parallel check. And so then you wouldn't be able to write a tangent plane to a surface because those functions would be like going in the same direction. All right, so finding the equation of a tangent plane. When you write the equation of a tangent plane, remember the equation of a tangent plane needs a normal vector. That's why we're doing the cross product. So because if you're writing a tangent plane, you need a normal vector. We're gonna have to do the cross product here. So the first thing you want to do, oops, I forgot to add in my point, at the point 2, 2, 3. Find the equation of the tangent plane to the surface. First thing you do is you take your partial derivatives. Okay, what is the partial derivative of R with respect to U for the first component? Gary. How about J, Kai? 0. And Nicholas, how about K? Partial derivative of U squared plus V with respect to U. 2U. Jocelyn, how about the partial derivative of I with respect to V? 0. Ben, how about J component? 4B. Karen, how about 1? And then our second thing that we're going to do is the cross product. Get that normal vector. Again, we're trying to write a tangent plane, so we need the normal vector. All right, and find the determinant. The only non-zero part is k for that first pass. And then we got 0 minus, oh man, not as easy that time, okay. So minus 8 uv in the I component and minus 1j. So you might want to rewrite it like in vector form if that's your preference. This is your normal vector. Those are going to be the coefficients. Of like the plane, like the ABC part, but you have to do it at that point. Okay, so we're doing, we want to go from having 3 terms to only having deal with U's and V's. So looking at your R, all right, so we've got X is essentially equal to what from R? U. Y is equal to 2v squared, and Z is equal to U squared plus V. All right, and we're at the point 2, 2, 3. So 2 is the X value, 2 is the Y value, and 3 is the Z value. So we can set these equal. It's pretty easy, I think, to solve for U in X, right? So U is equal to 2. What would V be equal to? Plus and minus 1. So then we have to confirm with Z which positive or negative V value are we using. So on Z we would have 2 squared plus what would equal 3? I think it has to be negative 1, right? Because you're doing 3 minus 4. So your U and V is going to be 2 and negative 1. Then plug that into your normal vector that you got. So we are using 2 and negative 1 in our normal vector to get the actual coefficient values. Okay, we got 16 -1, -4. It's A, B, C. Okay, so just to remind you, in a tangent plane, the n is the normal vector that we got from the cross product. What is x naught, y naught, z naught gonna be? 2, 2, 3. So we got 16x minus 2. The given point we got -1, y minus 2, -4, z minus 3 equals 0. If we simplified, should get down to 16x minus y minus 4z equals 18. I should probably type this part for next year. Okay, so if you have some surface the whole point of reparametrizing things that we were doing at the beginning of this section is to be able to find the surface area of like a cylinder or a sphere or whatever shape and use this formula, which is the cross product of the partial derivatives. The double integral of the cross product. That's the surface area formula. The surface area of a sphere with a radius of 4 that lies inside a cylinder with a radius of the square root of 2 and above the xy plane. So maybe I'll first try to draw that shape. You got sphere. Let me draw the planes first. No, sphere first. I've learned my lesson. I gotta do the circle first. Then I'll move my lines. Pretend that circle is 3-dimensional. Also, my x-axis looks like it's not quite straight. What happened there? All right, and then we got our cylinder. It's stopping on the XY plane. And we are saying the surface area of a sphere that lies inside the cylinder. So like the portion inside the cylinder. So if you imagine, the way I'm picturing this, because I'm drawing it terribly, is like one of those silos on a farm where you have the top of it, you know, like a, do you know what a silo is? Karen's looking at me. Oh my God. Yes.
Big metal can. Look like soda cans.
This is what I'm picturing. It's not zooming in, but that's what we're trying to find the surface area of. It's very busted looking. Okay, so we're like grain silo. We need to go from having 3 variables, because if we have a sphere, we really have x squared plus y squared is equal to z squared. Oh no, x squared plus y squared plus z squared is equal to 16. We want to go into we want to make a vector function that's only in spherical. Is the radius of the sphere changing ever? No. So then let's take this and go as a vector function. Probably actually need more space. So just take it from 3 variables down to 2 variables. The 2 variables you want to go down to are theta and phi. Okay, try to think about what you would make this be equal to. Chance, what do you think the first one's equal to? It's going to be x. What does x equal in spherical? Yes. Okay. Oliver, what do you think the y part is going to be? Good. And Chloe, how about the z part? Good. That's it. Okay. Then our domain. So look at the different parts of the surface area. We need to have the r function and we need the domain. So we had the sphere and then it's being restricted down to a cylinder above the xy plane. So your domain is basically that restriction that it's staying within. So let's kind of think of that and where it's going to intersect your, what's it called? Cylinder. So from the cylinder, what was the cylinder part equal to? Yeah, that was equal to 12. So where the sphere is intersecting the cylinder is what I'm trying to find. All right, so you get z is equal to plus and minus 2. We are dealing with being above the xy plane. So what do you think? Positive or negative 2? Positive 2. Okay. In spherical, z is equal to rho cosine phi. Right now we have z is 2 and rho is 4. what would phi be? And we're only taking the positive, like remember phi is between 0 and pi. So what would phi be in this case? Pi over 3. So we're starting at the top of the sphere, and we're tilting down to pi over 3, where they hit each other. So this point here is pi over 3 for phi. And where is phi equal to at the top? 0. And we're going all the way around the circle. So what do you think theta is between? 0 and 2 pi. Okay, we want to find the surface area. That's going to be the double integral of the magnitude of the partial derivatives, cross-producting. That's probably going to kill me. We're going to say u is like theta, and v is phi from our vector function. Okay. Derivative of that with respect to theta is going to be -4 sine 4 sine phi cosine theta 0. So it's going to be 4 cosine 4 sine -4 sine. Mm-hmm. Oh, should it be cosine? Thank you. You're right. We're just making sure you're paying attention. Okay, let's simplify. That one's going to multiply 0. Then that one's going to be doing quick simplification because that's going to. Okay, so that was the cross product. Next thing we have to do is do the magnitude of that cross product. What's 16 squared? 256. So you have 256 sine to the 4th phi cosine squared theta plus 256 sine to the 4th phi sine theta squared plus 256. What is each term? Can we combine any like terms, or maybe, oh, here, let's call your attention to something that's going on. Look at the numbers other than the sine squared and cosine squared on the first two terms. Are they the exact same thing? So we could simplify this to being 256 sine to the fourth plus the last term, 256 sine squared cosine squared. And then really this sine to the fourth is sine squared. So we can combine these to being the cosine squared and the sine squared to just being the square root of 256 sine squared phi, which is 16 sine phi. Hey, quick question. Isn't this the same thing as rho squared sine phi? Yeah, so could you have skipped all that if you realized that you were in spherical and just like jumped straight down from here and been like, wow, that is the multiplier for Jacobian. What a fun ride that was though, you know, like what a time to be alive. What an adventure. Yes. So you really, if you had realized, like, honestly, once you got here, you could have just jumped right into this. If you're in a certain space. So once you knew what the domain was, you could have just integrated it right away. And skip all that. But now you know how to do it if it isn't in spherical. If it's in like U's and V's, that's how you would have to do it. And the U's and V's are probably not going to be as aggressive of simplification as that. Okay. Good times. That was really good timing.